Welcome, dynamics students. This lecture includes a couple of examples of particle kinetics using curvilinear coordinate systems. So we're going to use a polar coordinate system, or basically cylindrical with z equals constant. And then we will use a normal tangent and show that it's effectively equivalent to polar for a constant radius. Again, we're going to be using our Euler's first law to say that any body can be approximated, or not approximated, can be literally defined as its center of mass from the standpoint of translational motion, and applying Newton's second law to that body's center of mass. And so we can treat it like a particle. So in this example, we have maybe a large ball or a small ball, but we don't care because we can treat it as a single point at its center of mass. And it's released from rest at an angle with respect to the horizontal, to this ceiling up here, of 30 degrees, and the cord is taut. Okay, that is important. And we can also assume that the cord doesn't stretch. We were told the fact that we were told that the cord is taut, and we're inferring that the cord doesn't stretch. This is going to have a big implication on whether or not we can say there's any motion here in the radial direction, which, lucky for us, there's not. And we are asked to find what the cord tension is during ensuing motion. So what that says is somebody wants to know, hey, can you give me the equation of motion for the center of mass of this ball as a function of tension, or tension as a function of the equations of motion? So we don't have to just create equations of motion. We have to create equations of motion and then basically get tension onto one side of the equation. But let's start with just finding the equations of motion. Then we can manipulate them however to express them, tension as a function of, in this case, theta position. So we really want rope tension as a function of theta. So again, steps to solving these problems. 1, establish a coordinate system that makes sense and makes things as easy as possible because they're already hard enough. 2, FBD, the body, or in this case, the point at the center of mass of the body that we care about. Use the sum of the forces in each of our coordinate orthogonal directions to equal the mass times the acceleration in that direction. Then we have those, isolate those accelerations, start integrating and pulling in initial conditions to create equations of motion. Now, as usual, we have to use some other piece of information to simplify our mathematics and to solve for all of our unknowns. So in this case, we're going to be ending up functioning on the fact that our path is effectively circular. That cord isn't stretching. So we're going to incorporate that in when we write out our equations of motion for our polar coordinate system. And that will simplify our math quite a bit. So not surprisingly, I've picked a polar coordinate system. So I have my r unit vector here, e little r hat, going outward, and I have my e theta increasing as we go clockwise. So there's my coordinate system. So tension is pointing directly in the radial direction. So I do not have a specific FBD because the schematic is very, very simple, but I'm going to go through my FBD anyway, and this time it's r theta instead of I hat j hat. So in the r hat direction, I have tension. In the negative r hat direction, and I have mg sine theta pointing in the positive r hat direction. So those are represented down here. The sum of the forces in the r hat orthogonal direction is mg sine theta minus t, and looking in the theta hat direction, I only have one force resultant, and that's my mg cosine theta. Going this way. Okay, so this is the resultant from my FBD. Here's the sum of the forces in those two orthogonal directions. Okay, so now we need expressions for acceleration in the r hat and theta hat direction. So let's do a quick review of our cylindrical polar coordinate system. The position of my my center of mass here at any time is literally going to be however far out it is in whatever direction my r hat vector is pointing. So my position at any time is, in this case, the length of the string L out in the direction of the r hat vector, wherever that happens to be pointing. If I want the velocity at any time, I just take the first time derivative of this expression, and I get the time derivative of the string length L times my unit vector in the r hat plus my string length times the first time derivative of my unit vector r hat, which is, we learned in our kinematics studies, is d theta dt times my unit vector in the theta direction. Remember, the derivative of a unit vector ends up being the perpendicular to that unit vector. So the first time derivative of my r hat vector is my theta hat times theta, first derivative of theta. So I have two terms here, and I can remind myself that the string's not stretching and it's not snapping, and it started taut, so dl dt is going to end up being 0, so I'll be able to cross that term out. So to get acceleration, which is what I really need to relate to these terms up here, I take another time derivative. So I took all the time derivatives just for practice, even though a lot of these are going to be 0 because L isn't changing with t. But if I were going to say it wasn't, or I wasn't sure, I would just take the time derivative of all of these expressions. So I would have d squared L dt squared times r hat. Then I would add dl dt times r hat dt, which would be another d theta dt in the theta direction. And then I would look over at this term. It goes three ways. I'm going to end up getting three time dependent terms out of this. I'll end up with a dl dt times d theta dt in the theta hat direction. Then I'll leave theta alone, and I'll multiply that by the time derivative of this term, which is d squared theta dt, or the angular acceleration, times theta hat. Then I end up with another added term of just L times d theta dt, or, by the way, that's also known as omega, or the angular velocity, times theta hat time derivative. So just like we found that the time derivative of r hat was theta dot times theta hat, the time derivative of theta hat is negative theta dot r hat. So same thing, it's perpendicular, but going in the other direction. So that ends up over here. So if I collect all of those terms together and collect r hat and theta hat terms, because I'm going to want to compare them to these forces up here, I end up with this full expression for acceleration. So if I did a big square and said, okay, that's the acceleration of this sucker at any time. I don't care what's moving. If I had an equation for d squared L dt squared, or L at any time, I could take the two derivatives. If I had expressions for all of these time derivatives, I'm there, because I could multiply this by m, collect terms, and compare right up here, which I'm going to do. But first I'm going to get rid of all of the things that aren't changing. So that's 0. String's not stretching. String's the same length. Theta's changing. That's cool. So I end up with one term in the r hat direction, which I'm going to equate up here to the force resultant there. That's 0. So this whole term goes away. And so This is the only term that I have that is going to equate to my forces in the theta hat direction. So that makes my life much easier. And if I were to write out the entire acceleration expression without the zero terms, this is what I would get. So I have a single term each in the r hat and theta hat directions to equate to my force sums in those directions. So this is great. So I'm going to go ahead and apply Newton's second law in the radial direction. So I have mass times my acceleration in the radial direction. So I'm going to circle that and just show right where it drops in. Boom. Everything in those parentheses. So mass times acceleration in the radial direction equals the force sum in the radial direction. Cool. So effectively I have satisfied the question right now. Believe it or not, this is an equation of motion. It's a differential equation, but it is an equation of motion. This is something to remember. The rest of our work now is going to be to find relationships that make it easier to solve this. But this is an equation of motion. So let's go ahead and do the same. Apply Newton's second law in the theta hat direction. So we've got, here's our acceleration in theta hat. We're going to multiply it by mass, equate it to my force sum from my FBD, and now I have another equation of motion. So I can say that basically I could cross out these and say string length times the second time derivative of theta equals g times cosine theta. And this is a rearrangement of that expression with 0. So this is basically, this is my Newton's second law application to the theta direction right here. So I'm going to use a math trick to make this a little bit easier to see. This is basically second derivative of theta. This is just a single expression for theta. I'm going to look for an expression that if I took the derivative with respect to time, I would get this. So to make that a little bit easier, I'm going to multiply both sides of this circled equation by d theta dt. So I'm going to multiply d theta dt by this term, by that term, just like we've shown here, and then by 0 and still get 0, surprisingly. And if you look at what's in these brackets here and say, okay, what would I take the derivative of with respect to time to get this? So we've got, if you said d theta dt equals x or something, you could say, okay, well, I have x and I have basically dx dt. What would I do to integrate to say what time derivative would give me that? So we're kind of using some very basic calculus substitution kind of chain rule concepts here and say, well, if I had d theta dt squared and I took the derivative of it and I multiplied it by 1/2, I took the derivative, the 2 and the squared would come down and give me a 1. I'd end up with d theta dt, and then of course I'd have to take the time derivative of d theta dt, which would give me, d squared theta dt squared. So I can use that same logic over here and say, if I had GL times, say, sine theta, I took the time derivative of that, I'd have a constant times cosine theta times d theta dt, which I just had here when I multiplied. So I can use some real basic integration strategies for this, having already, the trick was to multiply both sides by the d theta dt, which, by the way, we really only got away with because we had a 0 on this side. So we are conveniently using a rearrangement of our Newton's second law expression to get a 0, and then apply a few calculus integration tricks to get us something we can integrate with respect to time. So we can end up getting an algebraic expression for theta and t, and not a differential expression. That's all we're doing at this point. So we integrate with respect to time, and of course just get what's in this parentheses here. So we end up with d theta dt squared times 1/2 minus gravity over the string length times sine theta equal some constant, because we had to integrate for a constant. Here's the velocity. We started at rest, didn't we? And we started at 30 degrees. So we actually can evaluate this constant using our initial conditions. So the constant is actually negative g over 2L. And the nicest thing here is, here's d theta dt all squared. First derivative of theta with respect to time, total thing squared. What were we asked for? We wanted an expression for tension in terms of position, theta position. And we ended up, got to erase some stuff here. We'll go back to our Newton's second law expression in the radial direction, because that's where we had tension. So if we look at that back up here, we had this d theta dt squared, which was the only thing that was stopping us from saying, hey, we're done. Well, we can use this, which is all algebraic now, and just substitute, isolate d theta dt or squared, and just insert it right here in our first equation that we got from our first application of Newton's second law in the radial direction, and we're done, which is what we do. So we isolate d theta dt squared and use our initial condition evaluation of this constant, and we have 2g sine theta over L minus g over L. Plop that in right here, and we end up getting tension at any time is mg, so the weight of the body times 3 sine theta minus 1. Not necessarily intuitive. So key steps. Coordinate system. It's moving in a circular path. Polar coordinates just make so much sense. FBD. Show which forces are working in the radial, which forces are working in the theta direction. Collect terms. Some of the forces in each orthogonal direction, just like you would do if you were in statics, except you know that they're not going to all equal 0. Write out an expression for acceleration in terms of your coordinate system. Yeah, some of these start to get pretty big, but that's okay. It is what it is, and you're going to find something in the problem to make it solvable. In this case, the fact that the string was constant, the very thing giving us the circular path, simplified our acceleration expression for that coordinate system. Collect terms, r hats to r hats, theta hats to theta hats, and after that it was just math, just a little bit of an integration trick to simplify the math and insert initial conditions to solve for our constant of integration. So that's what gave it to us.